Hi everybody! Why is it so dark and mysterious today? Well, it's because we're going to do a lab! Alright, the lab we're going to do today is the absolute versus apparent magnitude of stars lab. So we've been talking about stars a lot in class, and specifically one of the things we're interested in is how bright a star is. But you can imagine, alright, are some stars bright because they're really close to the light? Hold on here, I've got my star. Because they're really close, well, that star's bright, right? Or is the star really, really far away, but at the same time it's just so big that it seems bright, right? And so that's the question that scientists have all the time, and that we want to kind of model with this lab for us today. So normally you'd be filling out the worksheet and doing a little graph for it. Instead of doing that, kind of like always this year, you're going to be answering the questions on the quiz. So here's the setup that we have going on here. Let me kind of spin everything around. We've got our star, right, which is just a lamp with a little tiny hole in it, right? So it's going to be our star, and we can have it set up so that the star, let's see here, is just about at the 0 centimeter mark on our meter stick. Right, and then what we'll do is each one of the centimeters is going to stand for something being 1 light year away. Now, to measure how bright the sun is at different distances, well, that's where we've got our LabQuest computer over here. And the LabQuest computer over in, hold on here, over in this little corner right here, hold on if you can see it, over in the little corner right over here, that's where our light sensor is. So we can actually sense how bright the light is that's shining in it. So key to this is we've got our sun set up so it's kind of at the 0 center or 0 mark, and the light's kind of pointing right at that little corner. Let me get it pointed right at that little corner. What we need to do is calibrate our light meter, right? And so what scientists often do is they want to consider all stars. They imagine all stars as being 32.6 light years away from Earth, right? And so what I've done is I've got our sensor set up here at about 32, let's see here, 32.6 centimeters away, right? And then we can calibrate it by touching the screen. Hold on here, touch the screen, zero it out. There we go, so it says 0. And so now, you know, our example right here is that, you know, the star is at 32.6 centimeters away from the star. Then what we're going to do is we're going to take different measurements, how bright the light is shining, right, from different distances, right? So that's going to be the main goal of our lab here, is to take some data in. So let's see if I get this guy all set up. Hopefully you can see it. So if we start with moving the star really, really close to the source of light, right, at 10 centimeters, right, the star is at 52 lumens, right? So 52 lumens for, you know, 10 centimeters, that would be kind of like 10 light years. If we move it back to 20 centimeters away, well, look, now it's all the way down to 34 lumens. Right, move it to 30. We should be getting pretty close here. Yep, pretty close to 1 because we were just past 30 lumens. So 30 lumens is good, or sorry, 30 light years away is going to be 3 lumens. Right, if we moved it just a little bit more, it would be at 0. But the next one to check is 40. Right, so for 40, yes, now we're into negative numbers, right, as far as collecting some data. If we move it back to 50, well, we're even losing more. We're down to negative 10. Oh, negative 12. Switch to negative 12. 60 centimeters away, or 60 light years away. Well, we're continuing to get even darker. Negative 15. 70. It's going to be negative 19. Oops. 80 centimeters away. Here, 80 centimeters away is negative 17. To which case you're like, oh my goodness, what madness is this, right? When we were at 70 light years away, it was negative 19. When we were at 80 centimeters away, it's only negative 17. We've actually gained a little bit of lumens. And some of that could just be just where I'm standing, because when we get really, really far back, it gets pretty sensitive. Let's see, though, if we can get a trend that kind of continues overall. At 90 centimeters away, yep, we're at negative 22, right? So negative 22. So that kind of shows us, hold on here. So that's great data. right? Weird things happen, right? There are outliers that happen and everything, so that's what happened at 80 centimeters. But overall, we've got some really good hard data on our sheet here that's showing the further away we go, well, the less lumens of light that are hitting the sensor, right? So that's perfect. Right, and so that's showing you the apparent magnitude, right? It's showing you that from Earth, right, is a star, you know, a star might be super, super bright and shining really hot and brightly and everything, but if it's super far away, you and I might see it as a teensy-weensy little itty-bitty star, right? Whereas, apparently, you know, if there's a star and it's burning and it's not very bright, it might be kind of small, it might be kind of dim and everything, but if it's super close to us, like I was showing you at the beginning, it might look like a really bright star, right? That's the apparent magnitude that's going on there. But what scientists want to do is they want to study the star and be able to look at it from the absolute magnitude. They want to be able to say, okay, from, you know, 32 was Earth, you know, from about 32 light years away, what would the star look like? And then it's almost like you can imaginarily put all the stars next to each other, and then that's where the HR diagram comes in, right? Then once you know the, you know, the size and the brightness of the star and everything, that way you can fit it onto that HR diagram, and then you can categorize all the stars and see how they fit in, you know, comparatively to each other. All right, remember to take the quiz, and I'll see you in class.